Okay, now we have a talk by Alexey Vladimirov, which is one of the practitioners in Madrid. Talk about rapidity correspondence, please.
Okay, so Francesca asked me to talk here about something. So I decided to talk about this correspondence between soft and repeat number dimension because it's a topic which is kind of a bridge between, say, conformal theories and factorization periods, which we are doing now. So what is that about? As you can imagine, QCD is not conformal. However, it is almost conformal, as we know. So if you look, for example, at three-order QCD, so you can see some traces of conformal variables. Some amplitudes, for example, would be almost conformal or something like this. And actually, you can use it to find some relations and useful identities between different observables in QCD. And there are several examples. Of course, it's not a kind of not full QCD, but only I'm talking about the QCD. So full QCD is definitely not conformal. So there are several examples. So this probably first and one of the most famous is a relation between ESBA and developed kernels at higher loops. And maybe you don't know what is that, but there is this such stuff which was already understood in the 90s, and people at that time derived beta function corrections for these kernels. But kind of more examples, of course, this soft correspondence between soft numbers and repeat number dimensions, or for example, corresponds between decay logarithms and global logarithms in jet production in small x physics. And very recently, there appeared some paper which relates some 4-point operator with some energy jet-like production observables. They actually very nicely called this method, which I'm going to talk about, conformal bridge. So that's why actually I'm going to utilize this word, although during previous 20 years, people just didn't call this method in any way. So what is it about? So the idea is actually following. You start from QCD. Build something. You consider some particular operator. I don't know, let me call it O1, or some observable. It's actually perturbable. So you consider this observable, and then you looking for generalization of this object into some, let me call it for a moment, conformal QCD, from some other theory, which you can relate to QCD, but it possesses conformal values. And you have to generalize. So you still have this voice. Then, because it's conformal theory, you can use conformal properties, conformal transformation, whatever you can invent, and relate this operator to something else. Probably in conformal theory, actually, you have whole set of operators with the same quantum numbers, which are equivalent in conformal theory, but not equivalent in QCD. So, and then you go step back and get here the same operator, but in QCD. So, and this way, you're actually going to learn something about your operator O1 from operator O2 in QCD. So, here there are goals. First of all, is actually to find a couple of useful operators. Because if you just take some operator, most probably you will find some conformal generalization, most probably just it's not useful to do transformation with anyone. Second is, of course, to find a transformation from perturbative to conformal QCD. And what people actually use usually is QCD dimension. So let me start from this first problem. So how to go from perturbative QCD to conformal QCD, because since QCD is not conformal, we actually we first can generalize it to QCD in dimension. Which is not QCD, by the way. So because QCD is defined in 4 dimensions. But as you know, in perturbation theory, quite often we actually use dimensional regularization. So that's why it looks like kind of natural transformation. And here in the dimension, on our hand, we have a point, this sufficient critical point, where it became conformal. So if I draw this, kind of what people usually draw it. So this QCD dimension has two kind of coupling points. We have two parameters. So alpha s here and epsilon here. I will use d equal to 4 minus 3 epsilon. And there exists a line like that, along which this theory has conformal variance, so just store scaling variance, has its line when beta function equal to 0. Beta equal to 0. On the other hand, beta function is minus 2 alpha s epsilon plus beta 0 alpha s and so on.
But isn't it for positive, for negative epsilon?
I don't remember percent, but I think it's negative epsilon, but I'm not sure. But we should compute. Usually, we never go to particular numbers. We always work in the letters. So basically, epsilon is minus beta 0 alpha s. So beta 0 is negative, so it's positive. So this equation we could always solve with respect to epsilon. And then we decided, okay, so I'm going to use epsilon star, which is minus beta 0 alpha minus beta 1 alpha squared and so on.
I think
For this particular,
the signs are a bit messed up.
no, okay, don't take too serious the science. It's more like illustration. But this number of dimensions, so QCD restores d-dimensional QCD. It's important. Restores its scaling values.
Yeah, just have this memory it's in above dimension, but
So here we have our here we have our missing critical point. Basically, what you should do, you should the some critical operator from here, go first there, then do whatever manipulation you like to do with this inside of this information here, then go back and you. So as I talked, there are already several examples of such conformal which is a very nice name of these relations, and I'm going to talk about the response between software and economic information. So what is that about? So let me go here. We remember what is epsilon star, so it's in factorization theorems, particularly in Drell-Yan processing, is such a very interesting object which is called Drell-Yan soft factor. Drell-Yan soft factor. Which is we call S. It depends on one vector B, which is transverse vector. And it's like this. So let me just write it and then tell what it was. So this is Gibson line, which goes from minus light cone infinity along vector n, which is light cone vector, to 0 to origin, and then along another light cone vector to another infinity. And then you add the similar object, but translated by this vector B. So this is my book. So these brackets don't fix it up. So if I will draw it, so is my light pole. So I have something like this line comes from infinity along light pole to the origin. When it turns, go to another origin. Then they should shift it a bit by this light pole in some transverse direction. And then basically come from that infinity, oops, sorry, this point, and then come back. Usually, okay, kind of, it's supposed that we use some nice gauge such that field is 0 at infinity. But in principle, if you don't have this gauge, you should add here extra Wilson lines, and basically it's infinity kind of closed. So I would also put tracks here. So. Okay, why is it important? This object contains information about scaling of logarithms in process of Drell-Yan, and there are two types of scaling, which are actually related to the divergences of this object. So, one type of divergences is UV divergence, which is kind of quite important. UV divergences. There are two of them. One happens here, that we call point A, and now it happens here, B. So when you have some gluons exchange very close to this cast, you will obviously get customers dimension. So customers dimension because it's kind of orthogonal Wilson lines, but generally speaking, it should be something what's usually called gamma soft or depending on this one. And there are two of them. But there is some extra stuff which is called rapidity. Divergence, which happens when you actually take gluon from here to the other Wilson line and it goes to infinity. It's very special type of divergence, which appears only in that configuration. For example, if you radiate it to the same Wilson line, you will get nothing, so it will just cancel because it's linear divergence. But this kind of divergence exists. And let me call this point C, like point of infinity, and this point infinity E. So, and you can see that you actually have also two repeat divergence, because you can radiate gluons like this, or you can radiate gluons this direction. So there are two repeat divergences, and the corresponding numerous dimension are usually called D, and we define to form the vector P. And there are also two of them. Okay, this object people knew how to work with that time when it was invented, so actually that was kind of a bit fast-ish, because it was people understand how to do it, they compute already a couple of loops, but what to do with it, which properties have this finite numerous dimension, people didn't know. By the way, it's exactly called rapidity numerous dimension, or in our terms, Collinsworth term. So here comes our conformal picture. So let's generalize. Okay, it's quite obviously this object to D-dimension. And I will think that my P is quite small, such that I can use perturbation theory. Because of course, if P is very large, so all perturbation breaks. Okay, I have this object in D dimensions, which I think is conformal. Then I can make a conformal transformation. And particularly here, yes, let me write this finding conformal transformation. We can invent some combination of transformations. So if you think about life on coordinates, it transforms like this. Minus 2a, a is some parameter, w is another parameter, 2ax plus x minus plus ax squared, lambda plus 2ax plus then x squared. Oh, this solution. Looks strange, but I assure you that this is actually a combination of translation, special conformal transformation, translation is parameter R, special conformal transformation parameter lambda, and then translation back. And you can also build the same, I will not write it, but along vector and bar, so basically exchange. Why is so nice? Because it takes your point C, your infinite far away point C, which is actually transverse plane. So if you think about Riemann sphere, so take kind of farthest point of Riemann sphere and put it somewhere in the bulk of your field. This kind of you have your sphere and make rotation like this. So what happens? So let me here below draw the same object under this transformation, actually not under this transformation, but transformation kind of two transformation, first along n direction and then along n bar direction. So you'll get, we will first draw it and then so you will have, so here's point A, here's point B, and it's so you will get some finite object of that type. So here's some particular curve, which is not anymore straight curve, it's some basically instead of just line between A and B, right now we have some curve. But this point C and D are right now okay, kind of in the bulk of your field. So you have normal Wilson loop where each Wilson line has zero distance because all of them are all Wilson lines. And everywhere here you have kind of angles that we call this V1, this is V2, this will be the V1 tilde, V2 tilde. So they're not anymore parallel.
But all the segments are null here or not?
Sorry?
The segments are null, are in the null direction, or the segments of the line,
Yep.
are they in some light form or?
They all along light form.
Okay.
All of them. So it's a bit complicated to draw it, but the idea is very basically you just take this object kind of and join it here and then push it to the middle of your space. And this object is much simpler than that one. Because here actually you have just 4 UV divergences. So if you you can fully describe this object if you just know its UV divergences, there are 4 of them. Basically, point you have cast here, 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 and here. The only difference that right now this curve started to depend on this. So here it was just kind of cut between a kind of right angles. Now here you have cuts between angles V1, V2, the vectors V1, V2. So only UV divergences over so basically which produces different combinations of numbers. So okay, since I'm talking already quite long, so let me repeat it up. So what's going on here basically? When you transform one object to another object, some kinds of divergences transform to another kind of divergences. And you have to actually accurately trace it. And you can trace that indeed the divergences of these divergences, of course, transform to divergences here and here, there is no change. But the big divergences, and it's more complicated to show, that actually transforms to, say, divergence of that kind which I draw here, like between B and C, transforms only to the divergence at point C. And corresponds the second divergence transforms to the divergence at point. So that's why, and now let me this part. We actually have very nice relation. If we would leave in conformal mode, we will say up to factor 2, which I don't remember, that cast anomalous dimension in V1 and V2 is equal to rapidity anomalous dimension with B. Where with B and V, you can just compute applying this relation between B and in vectors V, you can compute applying this. Basically, more or less, product of V1, V2 after this transformation is B squared multiplied by some number. U from A down. So, and these things actually here, remember it is factor 2. 2 is just because of definition how people define anomalous dimensions. Because in different parts of field theory, some people define this with 1, some people define with 1/2. So it appears that actually proper definition. So we have exact relation in conformal regime. Okay, now let's go to Wilson. Sorry, from Wilson-Fisher critical point to normal. So actually, okay, that means that in QCD, let me again put another box. We have gamma s V1 V2 equal to 2 d b of epsilon star. Why so? Because anomalous dimension in a mass bar scheme, as we know, are not dependent on your dimension. So it's something which is defined, transferred. Well, D depends on number of dimensions. So actually, generally speaking, such kind of relation due to this conformal bridge, you usually have epsilon star from both sides. So we have some object computed in this at least Fisher critical point equal to another object computed this Fisher critical point. But however, here it's kind of much more simple because you have just epsilon star from one. So what it helps, how it helps us, okay, you can immediately gain all one loop. So if, for example, you know that expression as, say, 2 loop, and you know that expression at 1 loop, you immediately have to compute this expression. If you know this expression at 4 loop, and you know this expression, for example, 3 loop, you can immediately compute this expression at 4. That was how it's actually the last computation of this point superkernel were done. Because computation of custom anomalous dimensions is kind of simpler. And people just compute this stuff at 3 loop plus 1 correction in epsilon. So you should not stop, but you can compute correction in epsilon. And using full anomalous dimension here, we just start.
So you can explain a bit more. So you have epsilon star, you can express it, I guess, as a function of the coupling using the beta function. What's it?
How do you let me give an example. Yeah. So actually, this gamma, for example, 1 is alpha s of 1 plus alpha s squared gamma 2 and so on. This guy looked before the correction of how it looks at 1 loop, but 1 loop actually looks like this. So it's very simple expression. You can compute it. It's b squared mu squared in power of epsilon gamma 1 minus epsilon plus epsilon plus alpha squared something. So now what you should do? So you should actually take your epsilon star, which was written here, minus beta 0 alpha s and so on. Substitute inside of that part, expand it. You will get something like let me call it kind of d1. So one loop threshold point plus, so it's this alpha square, and here you will get beta 0 d1 prime, which comes from Taylor expansion of that object at epsilon going to 0 plus d2. And that should be equal to your gamma 2. So it immediately gives you what is d2. Basically, your d2 then is gamma s, gamma 2 minus beta 0 d1 prime. So if you know that object at loop, you know one loop threshold, you for free get two loop threshold corresponding. And it really works. So actually, when I realized it, so I immediately computed two loops because it was already known that two loop and two loop I did. But it's actually kind of nice, but not the most important contribution from this side because, okay, I don't have time, so let me just list because kind of there are many consequences in this relation. Because you can study kind of separately one or another and get some general statements and transform them using this kind of relation one to another. So what is the, okay, I will just list them.
And the original physics of the blue one going to infinity, that's kind of as no translation. How do you translate that? To epsilon, the theory, the conformity. I mean, they are both UV divergence.
Inside, so when you transform it, they both will be divergence. But when you have some kind of in this funny object with infinitely some lines, you do something to see it's a strange object. On this strange object, you get some strange divergences. Some of them are special, they're called repeated divergences. They appear only in that configuration. So they not appear in, so you really have to take blue and radiate it to transfer this to infinity.
But by the way, could you also just have two lines instead of having this? I mean, you put also some cusps at finite, but you would also have just two non-lines and you would have this divergence or not?
No, if you have two parallel with lines, you will have zero because they are both on the same light plane. So you radiate blue between them and it will vanish.
Okay.
You really have to radiate from something which is kind of, you have to have basically some operator here. It could be different operator. Actually, there are very different objects. And then you have to radiate it to, actually not to the same Wilson line, but to next Wilson line. Because if you radiate to same Wilson line, it will be linear divergence.
So they need to come from the other direction.
Yes, you should have some special with b distance, transfer distance. And linear divergence usually cancel. If you have some normal object, we just cancel. But this get not cancel. And we know now we understand why, because it actually corresponds to some kind of on Riemann sphere, it corresponds to UV divergence. Okay, so just in addition to this funny gain of one loop computation, what you can do also. First of all, actually you can prove that repeated divergences multiplicatively generalizable. Why it is important? Because now you can prove your factorization theorem. So we did discuss factorization theorem, but without actually this statement, people just basically computed. Look, okay, one loop it cancels, two loop it cancels, and so on. But to prove that all orders, you must do some general statement. And if you know that it is multiplicative, and all this perturbation theory you can do. How to do it? I will not show it, but basically you have to build iteration. So you suppose that okay, you know that it is multiplicative at one loop, which is very simple to check, and then you know that this is multiplicative at all loops, and now you can build iteration and show that all loops will multiplicate. So what else? Actually, you can consider even more general object, which is called multi-factor scattering soft factor. Basically, it's when you have same kind of staples of Wilson line, but many of them. It corresponds to multi-factor scattering. And then, so let me kind of, I will not draw it in full glory, but we have many such Wilson lines. All of them kind of at this Riemann sphere meet some intervening point. And you can basically think that it's also in final, and then in finite volume. But basically, here you have say as many custom dimensions as you have discussed. But then we still have only two repeated divergences. One associated with this stuff, another associated with this stuff. So this is what called soft matrix of soft anomalous dimensions. because this normal dimension actually depends on color and this whole matrix. And again, you can actually relate in the same way, but this will be numerical matrices. Or matrix of normal dimension to matrix of rapidity. Which was actually very nice because at that moment, there was only one loop computation of matrices of rapidity normal dimensions. And immediately, kind of again, for free, I got it at 3 loops. Which was not trivial because at 2 loops it's kind of just dipole interaction, but at 3 loops you get really some multi-part interaction and many nice stuff to that. And extra, so okay, so far we got everything from soft normal dimension to rapidity normal dimension, but we actually can do it kind of get some information from here to here. Particularly, it is known that this normal dimension, gamma s, if you consider many mixed lines going on, so for example, in jet production, it has structure like this. So it has in color space, it has structure like first you have all dipoles, and here you sum in that we call dipole, and you sum over all possible A and B. It basically responds to just interaction between two Gibson lines. When you go to say interaction with period Gibson lines, and you can think that okay, we have probably something like T8, TP, TC, and here we have some gamma 3-dimensional. But it is known that it doesn't exist. It was proven by Sterman in 2006. But when you have, for example, some TA, TB, so interaction with 4 Gibson lines and so on. Of course, each next iteration appears at 1 loop higher, because you have to radiate at least 1 more gluon to connect Gibson lines. And eventually people became so powerful that we actually start to compute, for example, 5 Gibson line connections. And so on. However, using the fact that it is related with soft factor, you can immediately prove that there are never ever odd contributions to your jet production. So never a color odd contribution appears in your jets. So that all free kind of tripole color contribution was proven by Sterman that doesn't absent, but you can show it here that also there are no odd. How to do it? It's actually very extremely non-trivial on that side. Say if you look at work of Sterman, so he used huge amount of tricks to prove it. But on that side, for side of soft normal dimension, it's actually nothing else but consequence of the fact that your soft factor is independent, so is invariant under such rotation. So if you change just one lat pole to another lat pole, nothing changes. And it's sufficient to prove that all combination flows. So I believe that there are actually much more consequences of absence of odd color gel. But for the moment, I know only these 4. So actually, correspondence and these 3 consequences, but actually all of them are quite powerful. So and before this kind of conformal bridge was known, all of them were considered like some magical results, so which no one knows what to expect. So that's all what I wanted to present. I took a bit more than 15 minutes. Sorry. Thank you for your attention.
Are there any questions from Alexey?
I think since it's very well known stuff, so no questions.
So if you go outside the perturbative regime, that relation in some sense is difficult, or
Outside of perturbative regime, I don't know what is QCD in D dimension. So kind of. I don't know what is even a propagator gluon outside of perturbative regime. That's why I think all this discussion is only valid for perturbative question. Although, of course, it's interesting because sometimes, for example, people discuss, say, the modes, the summation of corresponding poles, which actually comes from powers of betas, sorry, from expansion of your charge in expansion of beta. Here, basically, what you're doing, you exactly extract your beta function in its contribution to all orders of your computation. So in some sense, it's actually probably more powerful than the normal estimation, and can tell you something about power functions, because it almost uses the same powers. But this is unexplored, so it's just kind of discussion for 5 years, and still the discussion is still there.
Does it say something on the fact that when you have a forced jet, the things do not factorize?
Actually, yes, one more point.
Yes.
Sometimes you can show absence of factorization. Particularly, there is such stuff as, you know, Gluon-Weizsäcker-Williams distribution, which actually is a finite operator. So it's like, it's just one single electron, and you put one gluon field, another gluon field, like FDU, and FDU alpha here, and you have bits and lines which go in a loop like this. Okay, kind of people derive it, but never test because it's very complicated object. How is it actually cancellation of logarithms or not? The answer is okay. At one loop it is, but beyond one loop it will never happen because if you do the same stuff and translate it to this plane, you actually get instead of this stuff, you'll get basically this kind of this transformation which you just draw. It will break this Lisa lines. Instead of this expression, you will get something like it's very difficult actually to draw. Basically. So this plan and applies form, it will put this point here and this point also here. But with this lines will approach right now from different infinities. And then close somewhere on that side. Why is that problematic? Because here you suppose that you have just repeated divergence here, repeated divergence here. There may be some bunch of UV divergence around those points, special points. But here you see that actually that repeated divergence is not factorizable from this repeated divergence. Because, okay, at one loop you will not see it, but starting from free loop, you will get quadrupole contribution, which will actually mix with error. And you will not be able to factorize your 4 jets if you wish to that.
Can you state more generally factorization occurs only when the conformal Fourier transformation is good enough?
This is kind of far-going statement. I will not do it so probably. But at least so you can use this trick to study your object. So if you see that something is not factorizable conformal to Fourier, it's definitely not factorizable to HeI. Vice versa is not necessarily true. Maybe something is factorizable conformal to Fourier, but not factorizable to HeI, as can mention. But I would say each object should stand separately. Okay? I would be on the safe side. Not making very high announcements.
Suppose you have another process, for instance, which you don't know its factorizations, like photon which goes to 2 quarks. Then it's a kind of T channel instead of an S channel. Then you can have emission of gluons from the emitted quarks and so on. And I think the soft factor that you have is the same one. That
If I remember, in that case, you have soft factor, which is basically just a triple of Wilson lines, pointing to infinity, right? There is no problem with that soft factor at all. You see, here, why that one particular configuration was kind of problematic because this infinity, so sorry, this is basically the same line on line. So in your the process which you're right now discussing, so it is for general kinematics, we have 3 different directions. So this is something very different. You cannot easily put here. But then people really start discussing small X regime and they see, okay, there is some particular this Weizsäcker-Williams CMD, which should look like that. I don't know why. No, but that is no. If you have some such stuff, it's factorization problem. And you can see just from consideration of this object alone, you cannot analyze them.
No, maybe you want to ask for curiosity more. You mentioned that you can have this relation with epsilon on both sides. But is it on the same? Does it give you a prediction that the same? Of course, you can do the computation, but Somehow again, it seems you're gaining something more because on the left-hand side does not depend on it.
Yes, it's still kind of statement is still valid in the sense that you have to compute one side, say up to n loop, and another side up to n minus one loop, and you learn nth loop just from that relation. But here it's kind of it will be not that simple because you will need to also complete your power suppression expansion in your case. But usually it is not complicated. They say if you compute a free loop and you compute up say final path, it's usually cost practically nothing to compute just it per dimension more. It's of course not absolutely simple, but it is not like making full computation. Because still you have free loop integrals, just have to expand one up to 1 power epsilon.
I was just thinking that the gamma s is like not depending. So if you can imagine that your function depends also on epsilon, then somehow then you have an equation. Derivative with respect to epsilon is 0. Then you can fix it in your QCT conform one.
No. But actually, the fact that normal dimension in the mass bar scheme not depends on epsilon is often used to study the evolution, because when you study this the rapidity of QCT exactly where it is to GPR, because normal dimensions appears to be conformed, and the object is not conformed, but it evolves as a conformed object, which is kind of nice. And then sometimes you can find special lines of evolution, which are kind of more special than others.
This sort of correspondence between these two different theories being used for other observables?
Yes. That's exactly what I told in the beginning. Probably it was not clear, but there is a very nice example, which I think is more powerful than that, but less studied. There is exists such stuff which is called Balitsky-Kovchev equation, which describes nonlinear evolution of QCT in the regime of small x. And there exists such stuff as global grid. It describes a particular kind of boundary behavior of logarithms in jet production. So it's two very different regimes. And actually it is that basically the same relation connects them. Okay, not exactly the same, but very similar. But however, there are problems because people in these communities they do it in very different manner. So it's very difficult to see. It's another example is recently using, actually we didn't use transformation, but we use the fact that in the Gibson-Fisher critical point QCT restores the conformal variance, people computed operator fraction expansion for deeply virtual complex cavities at all powers. Because it's kind of sufficiently simple process, such that in conformal field theory, operator product expansion is just given more or less by some kind of formula. But in QCT, it's some infinite amount of operators. And they will just kind of studied conformal anomaly and adding this anomaly from going here to here, and they got this full expansion. And there are a couple of more. But yeah, very nice. I would say every 3-4 years appears one more example. So since it's not extending hot topic, so just it's like this.
Okay. Let's thank again Alexey. So let's make a break of 10 minutes. Then we'll come back with the last topic.